Imagine a heavy truck driving across a bridge. The sheer weight of the truck is immense, and yet the bridge holds firm, allowing the vehicle to pass smoothly. This scenario is a testament to the marvels of modern engineering and the principles that keep our infrastructure safe and functional. What keeps the bridge from collapsing under its weight? It's a combination of design, materials, and precise calculations. Engineers spend countless hours ensuring that every component of the bridge can handle the stresses and strains it will face. The answer is good engineering. From the initial blueprints to the final construction, every step is meticulously planned and executed. Engineers use advanced software to simulate different scenarios and ensure the bridge can withstand various forces. Bridges are designed to handle the force of gravity pulling down on them. Gravity is a constant force that affects everything on Earth, and bridges are no exception. The design must account for this downward pull to ensure stability. Gravity is a powerful force, and it's always trying to pull everything towards the center of the Earth. This includes not just the bridge itself, but also the vehicles, pedestrians, and any other loads it carries. This includes bridges and everything on them. The weight of these loads adds to the gravitational force, making it crucial for the bridge to be designed to handle these combined stresses. To counteract gravity, bridges need to be strong and stable. Think of a table. Just as a table needs sturdy legs to support its top, a bridge needs robust supports to hold up its deck. The tabletop is like the bridge deck, and the legs are like the bridge's supports. These supports are crucial in distributing the weight evenly and preventing any part of the bridge from bearing too much load. The legs hold up the tabletop and prevent it from falling down. Similarly, the supports of a bridge hold up the deck, ensuring it remains stable and secure. Bridges work in a similar way. They have strong supports that are designed to handle the weight of the bridge itself, as well as any additional loads it may carry. They have strong supports that distribute the weight of the bridge and anything crossing it. These supports are often made of steel or reinforced concrete, materials known for their strength and durability. These supports transfer the weight down to the ground. The foundation of the bridge is equally important, as it must be able to handle the transferred load without shifting or settling. This way, the bridge can handle heavy loads without collapsing. Engineers conduct rigorous tests to ensure the bridge can handle more than its expected load, providing a safety margin. Engineers carefully calculate the forces acting on a bridge to make sure it can withstand the weight. They use mathematical models and physical tests to predict how the bridge will behave under different conditions. They want to make sure the bridge is safe for everyone. By understanding and applying the principles of physics and engineering, they ensure that our bridges remain reliable and secure for years to come. When we talk about bridges, we often use the words load and stress. But what do they mean? Load refers to the weight carried by the bridge. This includes the weight of the bridge itself, traffic, and even snow or wind. Imagine putting heavy books on a shelf. The books are the load on the shelf. Stress is the internal force within the bridge's materials that resist the load. Think of squeezing a sponge. The force you apply with your hand is like the load, and the resistance you feel from the sponge is like the stress. Engineers carefully consider both load and stress when designing bridges. They use strong materials like steel and concrete to handle these forces. They also design the shape and structure of the bridge to distribute the load evenly. This ensures that no single part of the bridge experiences too much stress. By carefully balancing load and stress, engineers create bridges that are both strong and durable. Bridges aren't just affected by gravity and the weight they carry. They also have to withstand natural forces like wind and earthquakes. Wind can push and pull on a bridge, creating vibrations and oscillations. Earthquakes can shake the ground violently, putting immense stress on a bridge's structure. A famous example of what can happen when these forces aren't properly accounted for is the collapse of the Tacoma Narrows Bridge in 1940. This bridge, located in Washington state, was nicknamed Galloping Gertie due to its tendency to sway in the wind. Sadly, just a few months after it opened, the bridge collapsed during a windstorm. The collapse was captured on film and remains a stark reminder of the power of nature. The Tacoma Narrows Bridge disaster taught engineers valuable lessons about the importance of considering aerodynamic forces and designing bridges with greater stability. It led to significant advancements in bridge design and engineering practices. Section 4. Strong and steady modern materials in bridge construction. Over the years, bridge building has evolved dramatically. From the rudimentary wooden structures of ancient times to the stone arches of the Roman era, each period in history has brought its own innovations and advancements. The Industrial Revolution marked a significant turning point, introducing iron and later steel as primary materials. This evolution has not only changed the way bridges look, but also how they function and endure over time. Today, engineers have access to a wider range of materials and construction techniques than ever before. The advent of computer-aided design, CAD, and other technological advancements has revolutionized the field, allowing for more precise calculations and innovative designs. These tools enable engineers to experiment with new materials and methods, pushing the boundaries of what is possible in bridge construction. One of the most significant advancements has been the use of high-strength materials like steel and reinforced concrete. High-strength steel, for instance, offers exceptional durability and can support immense loads, making it ideal for long-span bridges. Reinforced concrete, on the other hand, combines the compressive strength of concrete with the tensile strength of steel, resulting in a material that is both strong and versatile. Steel is incredibly strong and can withstand heavy loads. Its high tensile strength makes it an excellent choice for the main structural elements of a bridge, such as girders and cables. Additionally, steel's flexibility allows it to absorb and dissipate energy, which is crucial in areas prone to seismic activity. Concrete is durable and can be molded into various shapes. This versatility makes it suitable for a wide range of applications, from the foundations and piers to the deck and superstructure. Modern concrete mixes can be tailored to specific needs, incorporating additives that enhance its performance under different environmental conditions. These materials are often used together to create bridges that are both strong and resilient. The combination of steel and concrete leverages the strengths of both materials, resulting in structures that can withstand various stresses and strains. This hybrid approach is particularly effective in creating long-span bridges that need to support heavy traffic loads while remaining stable and secure. For example, many modern bridges use a combination of steel cables and concrete towers. This design is prevalent in cable-stayed bridges, where the steel cables provide the necessary tensile strength to support the bridge deck, while the concrete towers offer the compressive strength needed to anchor the structure. The cables provide tensile strength, while the concrete towers offer compressive strength. This synergy between materials ensures that the bridge can handle various forces, from the weight of vehicles to the impact of wind and weather. Engineers meticulously test these materials to ensure they meet the rigorous standards required for modern bridge construction. This combination allows engineers to build longer and more elegant bridges. The use of advanced materials and construction techniques has enabled the creation of structures that are not only functional, but also visually stunning. These bridges often become iconic landmarks, admired for their beauty as well as their engineering prowess. Another important consideration in modern bridge design is aerodynamics. The shape and design of a bridge can significantly impact its ability to withstand wind loads. Engineers use wind tunnel testing and computer simulations to optimize the aerodynamic performance of bridges, ensuring they remain stable even in strong winds. By shaping bridges to reduce wind resistance, engineers can minimize the impact of wind loads and prevent oscillations. This is particularly important for long-span bridges, where wind can cause significant movement and potentially lead to structural failure if not properly managed. The sleek, streamlined shapes of many modern bridges are not just for aesthetics, they serve an important structural purpose. By reducing wind resistance and optimizing load distribution, these designs enhance the overall stability and longevity of the bridge. In essence, modern bridge construction is a harmonious blend of art and science, where every element is carefully considered to achieve both beauty and functionality. Section 5. Smart Bridges, Sensors and Sustainability. We live in an age of technology, and bridges are no exception. The integration of advanced technology into our infrastructure is transforming the way we design, build, and maintain these critical structures. Engineers are now incorporating smart technologies into bridge design to improve safety, efficiency, and sustainability. These innovations are not just about making bridges stronger or more durable. They are about making them smarter and more responsive to the environment and the needs of the people who use them. One of the most promising innovations is the use of sensors. These small but powerful devices can be embedded in various parts of the bridge to continuously monitor its condition. Sensors can be embedded in bridges to monitor various factors, such as stress, strain, temperature, and vibration. By collecting this data, engineers can gain a comprehensive understanding of the bridge's performance and health. This real-time data allows engineers to track the health of the bridge and identify potential problems before they become serious. Early detection of issues means that maintenance can be performed proactively rather than reactively, which can save time, money, and potentially lives. For example, sensors can detect small cracks in concrete or steel before they grow into major structural issues. This early warning system is crucial for maintaining the integrity and safety of the bridge over its lifespan. This allows for timely maintenance and repairs, preventing costly and disruptive failures. By addressing issues early, we can extend the life of the bridge and ensure it remains safe for all users. Smart bridges can also adjust to changing conditions. They are designed to be adaptive and responsive, making them more resilient to environmental changes and extreme weather events. For instance, if sensors detect high winds, the bridge's lighting or signage can be adjusted to warn drivers. This can help prevent accidents and improve safety during adverse weather conditions. In addition to sensors, there is a growing focus on sustainability in bridge design. Engineers are looking for ways to reduce the environmental impact of bridge construction and operation. Engineers are increasingly using recycled materials and exploring innovative construction techniques to reduce the environmental impact of bridge building. This not only helps to conserve natural resources, but also reduces the carbon footprint of the construction process. By combining smart technology with sustainable practices, we can build bridges that are not only safer and more efficient, but also more environmentally friendly.